Before I introduce the speaker of today, I just want to start by acknowledging that I'm participating today from the traditional territories of the First People. We're participating today from land that is part of the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. And the University of Waterloo is located on that land that was granted to the Six Nations, including 6 miles on each side of the Grand River as part of the 1784 Haldimand Treaty. The University of Waterloo and its centres and institutes, like the Water Institute, are committed to raise awareness and contribute to Canada's Truth and Reconciliation Commission's calls for actions. So time to introduce the speaker of today. I'm very happy and honored that we have Professor Bill Mitch with us. He's a professor in the Department of Civil and Environmental Engineering at Stanford University. His research focuses on environmental organic chemistry, with particular interests in contaminant removal within treatment trains for the potable reuse of municipal wastewater, advanced oxidation processes, reactions of disinfectants, and seawater photochemistry. He obtained a BA in archaeology from Harvard University and a master's degree and a PhD degree in civil and environmental engineering from the University of California at Berkeley. He received numerous distinctions. I'm just going to mention one of them. He received the 2004 Outstanding Doctoral Dissertation Award from the Association of Environmental Engineering and Science Professors and Parsons Engineering, and a NSF Career Award in 2007. He served as the chair of the 2017 Disinfection Byproducts Cordon Conference, and he has served on the EPA's Scientific Advisory Panel's Drinking Water Committee. And today he's going to talk to us about challenges going from a linear to a circular water cycle. So I'm very happy to introduce Professor Bill Mitch. Let's give him a round of applause. Thank you.
Great, so if we think about our current water systems, they basically look at a once-use model. So we import pristine water, use it once, clean it up, and throw it out, and hopefully put to receiving waters in a clean enough fashion to not kill organisms in receiving waters. But some of our future reuse systems might look at this wastewater more as a resource. And so we can extract important resources, namely water, and so I'll talk about that today. That's now operating at full scale. We can potentially extract energy from the dissolved organics in wastewater. That I'll talk about today, some systems we're looking at pilot scale, and potentially also extract nutrients. And I'll talk about that today with respect to some lab scale experiments. So if we think about our current water system, we tend to focus on importing water from pristine sources, and often, particularly in California, from very distant sources. We bring it into a treatment plant, use it once, and as I mentioned before, clean it up, hopefully in a suitable fashion for discharge to receiving waters, ideally downstream of where we're living, so it's pushed away from us. Why do we need to change? Well, it turns out that this practice of importing water from distant sources is very energy intensive. So I'm showing down here on the US average, it's about 0.3 kilowatt hours per cubic meter to move water from these sources to the drinking water treatment plant. The drinking water treatment process itself is very low on energy usage, and a lot of the additional energy goes into pumping this water through the distribution system out to people's houses. So actually the transport cost is what matters most, not so much the treatment cost. Now that's on average, as I mentioned, it was about 0.3 kilowatt hours per cubic meter, but if we think about areas like California, it's much more extreme. So here is showing a map of California. About half the population in California lives down in the LA and San Diego area. And here we import water from very distant sources, so shown here in these kind of purple lines, bringing in water from the Owens River Valley, also the California Aqueduct, and the Colorado River Aqueduct. And if we think about the average cost of bringing water to LA, it's about an order of magnitude higher. So pumping these waters down into the LA basin is very expensive. What else is changing? Well, the climate's changing, and it used to be that drought was an abnormal happening. It's now routine. 7 of the past 10 years in California have been drought years. So at what point is that an exception rather than the rule? So just showing current practice, and last year you can see these areas of exceptional drought, these kind of very dark blobs on the map. What are the consequences of that? Well, obviously, for a water supply perspective, there are consequences. So you see a lot of pictures like this year after year of docks gone dry, reservoirs that were once full that now look like this. Similar shots of marinas that are basically ending up barely staying afloat. So there's impacts on water supply, but also has other impacts throughout society. So one is power. Electrical power. A lot of our power in California comes from hydroelectric. So if your dam's not full, you're also not generating a lot of power. And California is a big agricultural state. So a lot of the water in California is used for irrigating crops, and most of the sort of interesting things that are grown in the US are grown in California. Lettuce, tomatoes, that sort of thing, rather than just corn and soybeans. And so we start seeing routinely pictures like this, or here, where orchards are just mowed down because of no access to water for that year. So maybe instead of importing an unreliable source of pristine water to long distances to get it to drinking water treatment plants, maybe we could reuse the water within the system. And so when we think about trying to expand water supplies, the press tends to focus on seawater desalination. Some of the other options are stormwater capture. That means capturing the runoff that hits cities and cleaning it up as a water supply. But what I'm going to focus on today is wastewater reuse, and particular potable reuse. And so why reuse? Well, there's a bunch of reasons. Number one, it's a reliable supply. So stormwater capture sounds good, but the whole reason we're thinking about these practices is because it's not raining anymore. So that's an unreliable supply. And if we think about what goes on in a city, about 75% of the water that goes in a house ends up in the sewer. So it's about flow matched with what we need. It's secure from a legal point of view. So a lot of what goes on in California are fights between cities and states over who owns access to water. Well, this is your water. It's your sewage, so you have access to that water. And three, it's local. So again, hearkening back to the previous slides, the energy intensity of pumping water from distant sources, this water is already in your watershed or sewer shed. There's also some win-win scenarios here. So for a variety of reasons, regulatory drivers are pushing wastewater treatment plants to put in additional treatment to remove things like nutrients to prevent eutrophication. And there's discussion now about adding removal of perfluorinated contaminants from municipal wastewater. And so with these kind of drivers to put in additional treatment to the wastewater before you discharge it to an ecosystem, as long as you're doing that additional treatment, why not turn it into a water supply? And so there's pressures not just from the regulators, but also from other sort of NGO operations. So this is kind of an ad from the Surfrider Foundation, who obviously has a lot of concerns about surfing right off the shore where some of these wastewater outfalls are discharging. And so here they're showing kind of garbage, but there are also concerns about pathogens and contaminants that they're surfing in, essentially. So diverting these contaminants away from discharge to receiving waters can be perceived as a win-win scenario for beyond just access to water, but also for enhancing the quality of ecosystems. So wastewater reuse is one thing. Why potable reuse? Why don't we just use it to irrigate things like golf courses rather than turning it into a drinking water supply? And so we do have non-potable reuse systems throughout California. They're typically paint the pipes purple to alert people that it's not drinking water quality. So we often refer to it as purple pipe systems. But the challenge is you need a separate distribution system, these purple pipes. And that's very expensive to install. That's putting pipes in the ground, digging up streets is millions of dollars a mile. And so that can dwarf the cost of the additional treatment required to convert this low quality water into a drinking water supply. So why not go all the way to a drinking water supply where you gain flexibility in terms of the use? So over here on the right is a map of, here's the San Francisco Bay up here, here's San Jose or Silicon Valley. And the wastewater plant's right near here, near the Bayshore, and this is the purple pipe distribution system. So they do have these distribution systems, but they tend to cart the water out to high volume users, golf courses, nurseries, and that sort of thing. To expand beyond this to, say, pipe out to people's houses for irrigating their lawns becomes much more expensive than it's worth. So what's the central challenge? If we go for converting this wastewater supply, wastewater source into a drinking water supply, what's the central challenge? The central challenge is all the contaminants. So there's thousands, beyond the pathogens, there's thousands of different chemicals that are used in consumer products that are flushed down the toilet or end up in your shower water. We can't possibly monitor all of them. So how do we know when we've removed it sufficiently to turn it into a drinking water supply? And so what we typically do is apply broad screen treatment barriers. So if we can't measure individual chemicals, we can validate that we have treatment processes that remove a broad array of contaminants of certain characteristics. And the two flavors of that are the following. So in coastal areas like California, we tend to focus on a reverse osmosis-based treatment train, sometimes referred to as full advanced treatment or FAT. And so what this consists of are 3 steps: microfiltration. That's basically a glorified sand filter, so it's just a pre-treatment step. The heart of the process is reverse osmosis, a broad screen physical filtration barrier that ideally squeezes out everything but the water. And some things slip through, and so we follow it with something called an advanced oxidation process that basically generates radicals that ideally go after anything, whatever could conceivably slip through the membrane. And so typically it's ultraviolet photolysis of hydrogen peroxide to make this radical. In inland areas like Colorado, Arizona, those sorts of areas, they try to avoid reverse osmosis because part of the challenge is everything that's squeezed out of the water has to go someplace. And so disposing of those salts and contaminants in inland areas is problematic. Are you going to dump it in the river? Then it's going to float downstream to the next user. So instead, they try to avoid these membrane-based systems and use other barriers, such as ozone, kind of a broad screen chemical barrier, followed by biological activated carbon. So hopefully the microorganisms are eating whatever's left in that water. But I put down here, and the kitchen sink, because one of the first of these types of systems is actually in Namibia in southern Africa in the 60s. And so it's an inland area. And one of the challenges they had is that it's a desert. So evaporation far exceeds the rainfall. So they started mining the sewage essentially as a water supply. And so indeed, here's you have some surface water, but they're blending it with wastewater. And it goes through this treatment train. And you see the essence of what these inland areas in the US use, ozone and biological activated carbon. But they tack on many other treatment processes to hopefully knock back all the contaminants. So ozone's applied over here, activated carbon, ultrafiltration, and many other processes as well. So how does it, with all these treatment processes, how expensive is it? So looking at up here, we're comparing it to what the press tends to focus on: seawater desalination and also importing pristine water. And here we're looking at energy intensity. And so here are seawater desalination projects, such as some in California, very energy intensive. Here's conventional surface waters and groundwaters that appear fairly low, kind of near that low US average I was talking about before. Whereas here are our RO-free, this is in southern Virginia, so one of these kinds of semi-inland areas where they don't use reverse osmosis. Here are some of these California systems that use reverse osmosis. So seemingly higher than conventional sources, but when we consider that we're in California where the energy intensity of pumping water is much higher, these are actually cheaper, and cheaper than seawater desalination. And we can also see that on a cost perspective. So here's an RO-based Southern California reuse system versus seawater desalination. So when we think about what Southern California is looking into, it's mostly these wastewater reuse systems. So Orange County has the oldest one in the US since the 1970s, and also the largest system in the US at about 130 million gallons a day. Los Angeles announced a Green New Deal where by 2035 they hope to recycle 100% of their municipal wastewater, and to the extent possible through potable reuse rather than non-potable. And San Diego is also looking at generating about a third of their supply from potable reuse within the next less than 15 years at this point. All right, but then the question becomes, is it safe? So certainly there's problems because of its sewage origin. People don't want to drink toilet water. So back in the 1990s, San Diego first tried to recycle wastewater as a potable supply, and they got well through into the design process, and then the press got a hold of it with pictures like this, and that was the end of it. Things being, droughts arising and people getting used to the Orange County system, it's now back in play, and they're implementing or constructing some of these reuse systems in San Diego. How do we know that it's safe? So part of the problem is, as we mentioned, we have thousands of chemicals. What do we monitor? And which ones are the ones that matter? When do we say we're done? That's the key one, is you'll always find something in water. How do we know that it's safe enough? Because if we keep adding barriers, we ramp up the expense, and maybe for no meaningful benefit. So for example, California is now considering direct potable reuse regulations, where instead of what we talked about before, MFRO, AOP, they want to tack on ozone and biological activated carbon up front. Is that really needed? So keeping in mind that throughout the US and various other areas of the world, we have de facto reuse. That's unintentional reuse. And so one of the classic examples is Dallas and Houston. So here's the Gulf of Mexico. Dallas sewage gets dumped into the Trinity River, runs down to Livingston Reservoir, which provides Houston with drinking water. Well, on average, this is about 50% wastewater, and it's just gone through a conventional municipal wastewater plant, no fancy treatment. So for sure, there are contaminants that slip through that system that are entering Houston's water supply. So when we think about potable reuse, there's there's a well-developed regulatory framework for microbial quality in California. So California reuse systems are required to demonstrate that they get 12-log removal of virus and 10-log removal of things like Giardia and Cryptosporidium. And they have to validate through the regulators how they get this through the treatment train. So they can accumulate log removals across the treatment train. So this is a fairly well-developed framework. Chemicals are more difficult because there are so many, and we can't possibly monitor them all. So the public is focused on pharmaceuticals. Regulators focus on different chemicals. They tend to focus on industrial solvents, trichloroethylene, 1,4-dioxane, and various disinfection byproducts such as NDMA. And one of the reasons why, this is a table from a National Academy report looking at potable reuse and looking at different scenarios of reuse systems and from a margin of safety factor. So a high margin of safety means you're nowhere near a level of public health concern at the concentrations detected in reuse waters. And what do we see? Pharmaceuticals are in the millions. The chemicals that are at low margins of safety are things like NDMA, which is a disinfection byproduct, but it also shows up for other reasons, and various byproducts of disinfection, trihalmethanes, haloacetic acids, and other unregulated contaminants. And there's other chemicals as well. The other ones that tend to show up of potential concern are perfluorinated compounds down here. So we started doing a study saying when we get to the concept of we have de facto reuse, so your conventional water supplies often are impacted by upstream wastewater discharges, and they are going to have contaminants in them. So how do we know? There's a lot more scrutiny on the intentional potable reuse systems. How do we know when the treatment's good enough? And so we thought, well, let's just compare the quality of conventional drinking waters to potable reuse waters. And what we did was apply bioassays, so mammalian cell cytotoxicity. Cytotoxicity is a broad screen metric. It basically means your cells aren't growing as fast as they could have done, so many different modes of toxicity could contribute to that. And what we see for different reuse systems, both RO-based, like the California model, or RO-free systems, is they can be of higher quality than conventional surface waters, and in some cases comparable to groundwater systems. And so this is why are there contaminants here? Again, it comes back to the idea that we do have upstream wastewater discharges in a lot of our drinking water supplies. And even if you don't, you're disinfecting that water and you're making disinfection byproducts just from reactions of chlorine with the natural organic matter. So potable reuse, because it has much more extensive treatment, can reduce those contaminant concentrations. And I think one of the reasons why this is important are these discussions right now where I'm not so sure California has good rationale for tacking together all these treatment processes, other than a knee-jerk reaction that the more treatment is better. But it also drives up the cost. So what are the toxicity drivers? This is a little bit of a diversion, but we've also, with the same study, we're looking at what chemicals might matter. So as I mentioned, byproducts were priority chemicals from that margin of safety calculation. Regulators tend to focus on two classes, trihalomethanes and haloacetic acids. Researchers in the DBP field tend to focus on unregulated but small molecule DBPs like haloacetonitriles. So we looked at what fraction, these are just two of the studies we were looking at for that previous study, and what constitutes cytotoxicity. So we looked at the regulateds, the unregulateds, and the other. And what we see is frequently the other category dominates. So what's in that other? Well, right now it's pretty poorly defined. It's presumably higher molecular weight materials. So we started to look at what could contribute to the other pile. And there's kinds of two thoughts. So ultimately, organic matter, the precursors for DBPs, comes from organic matter shed from things like leaves, algae, bacteria, and watersheds. And they're made up of biomolecules. And a lot of the focus has been on things like lignin, structural polymers in wood, that degrade in water supplies to things we call humic substances that are poorly defined but contain aromatic groups. And the thought is that disinfectants react with these, break these bonds, liberate aromatic products that can then go on and be halogenated. Ultimately, these break down to these 1 to 2 carbon DBPs. So some people are looking at these. What we've been looking at is all cells also contain other biopolymers like proteins and lipids. These can react with chlorine, and so we should be able to form the associated byproducts. So tyrosine can form chlorotyrazines. Alkenes and fatty acids like oleic acid can form chlorohydrins. And indeed, looking at those same samples that we looked at before for cytotoxicity, we find these compounds out there. All right, so we can extract water, and that's happening at full scale with lots of plans going on in Southern California to expand the scale of that. What else can we extract from water? Well, one thing we can think about is that food, through poo, essentially, ends up in the wastewater plant as dissolved organic carbon that exerts biological oxygen demand. Currently, we put in a lot of energy through activated sludge systems to supply oxygen to essentially burn these organics to CO2. Do we need to be adding so much energy? And it can be a lot. About 50% of wastewater treatment is associated with that aeration step. So one of the alternative options is to try anaerobic treatment. Ferment the dissolved organics and generate methane that you can capture for energy. We do this for biosolids, but can we do it for the dissolved organics in the mainstream treatment process? Anaerobic bacteria are much less efficient than activated sludge aerobic bacteria. And so traditionally people said, hey, this can't be done because you need to hold the water just like you do for anaerobic digestion for days because these organisms are too slow. So we've been looking at a pilot scale treatment shown here in Redwood City. It's about 30,000 gallons per day that consists of this process where we're fluidizing a bed of activated carbon and a biofilm of anaerobic bacteria grow on the biofilm. So the heart of the process is essentially you're growing such a thick biofilm that you're making up for their inefficiency by having that many more mouths eating the food. And so how does it work? So we're currently meeting secondary effluent standards through this process. Here showing COD coming in and going out for different hydraulic residence times. We're currently operating around 5 hours for the total process. I forgot to mention, this also has, it's a membrane bioreactor, so it also has ultrafiltration on the back. So it pretty much easily meets TSS standards. But overall, the residence time is about 5 hours. That compares well with traditional activated sludge treatment, where you might have 6 to 8 hours in the aeration basin, followed by an hour or so in the clarifiers. So we're actually lower time overall to reach the same standards. And because it's lower overall time, we can shrink the footprint of the plant. We also produce fewer biosolids. Why? Activated sludge bacteria get a lot more energy per chunk of food, so they multiply more, and you make more waste cells that you have to dispose of. So with anaerobic bacteria, that's not the case, and for solids generated by the secondary process, we get a 90% reduction. Biosolids are a major cost to wastewater treatment processes, so we can shrink that part of the facility as well. So why this matters, particularly in areas like the Bay, is land is ridiculously expensive. And so we're showing here, this is the Redwood City facility right by the Bay shore. Here's their existing plant. If we put in one of these anaerobic systems, by saving on things like avoiding secondary clarifiers and reducing the size of the digesters because we're generating fewer biosolids, we could free up this amount of space. And this is valuable because cities like Redwood City want to do reuse systems, but they don't have the land to put in the RO membranes and the other things they need. So we're gaining back land by switching to this type of process. We also looked at energy use. So here's the energy consumption. We're avoiding aeration, so it's very low. Here's the net energy production if we capture the methane and turn it into electricity. So it's the first potential energy positive system as a wastewater treatment plant. Okay, so we talked about extracting water, extracting energy at pilot scale. What about extracting nutrients? So currently, we need nutrients for farming, and we generate it by taking nitrogen gas, putting in a lot of energy to generate ammonia. So a substantial amount of energy. Use it once, it goes through the wastewater treatment plant, and in many areas there is a motivation to remove that nutrient through nitrification, denitrification, converting that ammonia ultimately back into nitrogen gas, but it's also very energy intensive. So put the two together and we get a lot of energy in just to use that ammonia once and then throw it out, essentially. So could we capture it and reuse it in some fashion? So this is only at lab scale, but one of the things that's somewhat convenient about using an energy-intensive process like reverse osmosis is that it screens out a lot of molecules, particularly charged molecules. And if we think about ammonia, pKa of 9.3 at pH 7 or thereabouts for wastewater is predominantly in this form. And RO is very good at removing charged compounds. So that's why it can remove salts. It can also remove ammonium. So the ammonia gets rejected in the RO concentrate. So by extracting the water, we're also getting a freebie essentially by concentrating the ammonia and therefore making it easier to capture it and reuse it. How could we do that? So here we have the wastewater comes in, the ammonia is rejected into a lower volume of the influent water, and then we can take that and run it through an air stripper and capture it in an acid bath to further concentrate that ammonia for reuse. So we've looked at that process at lab scale, and you can get about 90% recovery through that type of process. So kind of putting it all together and thinking about comparing our current conventional linear system where we import water often from distant sources, use it once, put in a lot of energy to aerobic activated sludge type processes to burn the dissolved organics to CO2, and generate ammonia from nitrogen gas using this energy intensive process, use it for farming, and then get rid of it through nitrification, denitrification, versus a future linear or circular system where we extract water through potable reuse using RO membranes, do anaerobic wastewater treatment to ferment the organics to methane to capture for energy, and extract ammonia from the RO concentrate. We can look at it from an net energy savings. The net energy savings isn't huge, but about 15%. We can also think about greenhouse gas emissions between the two systems, and we get about a 45% reduction. Where are the greenhouse gases coming from? N2O comes from nitrification, denitrification type processes, And we're also reducing the electricity usage by avoiding that energy-intensive aeration step. There is some greater use of treatment chemicals for things like the acid bath and the air stripping type system. So it sounds pretty good overall, but are there challenges? Yes, there are. And so one of the key challenges for these anaerobic wastewater systems in particular is generation of sulfides. So before you get to fermenting the organics to methane, you'll have sulfate reduction, biological sulfate reduction, which will generate hydrogen sulfide. And this can be substantial. So in Redwood City, we get seasonal variations in sulfate concentrations due to different levels of the bay, essentially, and seawater intrusion into the sewers, of up to a millimolar sulfate. Well, that can be converted into a millimolar hydrogen sulfide. And so hydrogen sulfide is bad for several reasons. It smells like a rotten egg, so nobody wants to use your water. But probably, at least or more importantly, is that it exerts a lot of, hinders disinfection. There's a huge chlorine demand, and the UV absorbance by sulfides is also potent. So your two kind of main ways of disinfecting wastewater are out the window. So if we wanted to get rid of the sulfides, one of the conventional ways that we use is adding chlorine. But it's about a 4-to-1 stoichiometry, and when we play that out with the millimolar sulfide, what we're getting is 280 milligrams per liter chlorine. That's huge, way more than you'd ever apply to even disinfect wastewater. So that's prohibitively expensive. It also adds to the salinity because we're adding a ton of chlorine, which ultimately becomes chloride. So that could be difficult, particularly for inland areas where your chloride would wash downstream to the next user. And if you're adding this much chlorine, you're probably making a bunch of toxic carcinogenic byproducts. So an alternative that we're looking at is hydrogen peroxide. Hydrogen peroxide is about half the cost of chlorine, and it can operate in the following ways. It has a pH dependence where it reacts with H2S to make elemental sulfur. It reacts with HS- to form sulfate. And the stoichiometry is different, so you need about 4 times as much for this scenario. And the pKa is right around where we operate. So small pH adjustments can affect which way you operate. Here, you're using less hydrogen peroxide, but you make elemental sulfur. And that can go on, basically your water turns milky white, and any kind of downstream filtration process will have to deal with that elemental mud you're making. Here, you're making a dissolved compound, so that's okay, but the problem is you pay more. So we're doing pilot tests right now where we can say, here's our sulfide coming in micromolar, so almost a millimolar in the 2 cases, operating at pH 7 or 8.3. When we disinfect here or use hydrogen peroxide here, we can get away with a lower dose because we're operating at low pH, so we're operating in this regime. But again, we make a lot of elemental sulfur. At the higher pH, we're down here. And we make less elemental sulfur, but we make things like sulfite, and also this thiosulfate, so more oxidized products. Kind of getting towards the end here, one of the things we are also looking at is improving the energy efficiency of other components of the reuse train. So most attention for these potable reuse trains in terms of optimizing processes goes into optimizing membranes, making more efficient membrane materials, that sort of thing. RO, MF membranes, anti-fouling, that sort of thing. But it's kind of reaching diminishing returns. There haven't been substantial improvements over the past few decades in these membrane systems. So what about other components of the reuse train? Less attention has focused there. And so this is showing electrical intensity of different components of the reuse train. And yes, MF and RO kind of dominate, but there are other components that contribute, such as the advanced oxidation process. So the conventional way we do this is we have UV photolysis of hydrogen peroxide to make hydroxyl radical, like I mentioned before, that ideally goes on to tear apart any contaminant that makes it through your RO membrane. And we do this using low-pressure mercury lamps that emit at 254 nanometer. Nowadays, there's interest in other kinds of light-emitting diode-type lamps that can emit at different wavelengths. We've been looking at these kind of higher energy, lower wavelength photons, 222 nanometers. And the benefit there is hydrogen peroxide absorbs more strongly at this lower wavelength, so we can potentially have a more efficient system, more efficient photolysis of the hydrogen peroxide to make these radicals. So the question is, even though we're using higher energy per photon, if the photon is more efficiently absorbed, do we still come out ahead? So we can look at things on a fluence basis, units for UV dose, millijoules per centimeter squared, that already incorporate that energy component. And so what do people care about? They care for regulatory oversight. They care about viral inactivation, that log removal. We tend to spike waters with MS2 bacteriophage. It's a non-pathogenic model that you can use to validate viral removal. And for chemical targets, the targets for the regulators tend to be NDMA, which is this disinfection byproduct, which goes by direct photolysis, and 1,4-dioxane. It's kind of an industrial solvent that is taken care of by our hydroxyl radical. So here's what we see with 3 different full-scale reverse osmosis permeates at California potable reuse systems. On the viral inactivation side, we're looking at UV dose down here and log removal here. And what we see is that the 222 nanometer is about 30% more efficient than the traditional 254. Over here, we're looking at fluence-based rate constants at these different RO permeates. Side by side, the fluence-based rate constant, so how fastly you degrade the chemical 1,4-dioxane or NDMA by 254 or 222 nanometers versus 254. And in all 3 systems RO permeates, the 222 is about 3-fold more efficient than the conventional 254 nanometer. For NDMA, it's maybe a factor of 2 more efficient. But in all 3 cases, we come out ahead just by switching the bulb. Okay, so just a summary, our conventional systems are this once-use linear system that tends to be very energy intensive. We use a lot of energy to import water, pump it from distant sources, and a lot of energy to synthesize ammonia, to make fertilizer for growing food, and then after we use it, we put in a lot of energy to clean the water using these activated sludge systems, and to try to remove the ammonia through nitrification, denitrification processes. In a kind of future scenario, maybe we can look at sewage as a system to mine for resources in a circular water system. So we can mine it for 3 types of resources: water, latent energy from the dissolved organics, and the ammonia that's present in there. And so we saw as potentially we could reduce the energy use of the entire water cycle by about 15% and greenhouse gases by almost 50%. Some of the other benefits is that we gain water security. We're not as subject to whether or not it rains. We can leave, when it does rain, we can leave that water for ecosystems instead of piping it to distant cities. And we can reduce the contaminants that are associated with conventional wastewater discharges by diverting them from the discharge itself. So currently, we're operating with the water recovery at full scale through these full-scale systems throughout Southern California. Our local city is trying to put in about 5 of these reuse trains in the next, say, 10, 15 years. At pilot scale and lab scale, we're still looking at these kinds of other extraction methods, extracting the methane and the ammonia. And there are some challenges, though, that we have to overcome, such as how to deal with the sulfides. And so with that, thank you, and see if you have any questions.
Thank you. Thank you very, very much. That was a very interesting presentation. I especially like the question, when is water clean enough or safe enough? And I loved how you introduced economics in it as well. We have a number of economists here in the room who might have some questions for you about that. So we have around 10, 15 minutes for questions. Does anyone want to start? And when you have a question, please briefly introduce yourself, and Professor Mitch knows who he's talking to.
So I'm Nick. I'm an undergrad student, and I'm from the econ department, but this question is actually not very related to economics. Could you go back to that slide that had the component for leaves and for algae and for bacteria?
Where is it?
Oh,
Here.
yeah. So, I'm just a little bit curious that why wouldn't the component for leaves add up to 100%? Like, I mean, what else could you know?
Well, I didn't put down, or I did put down cellulose. There's other things in there, such as nucleic acids that I didn't put down. All cells have that.
Yeah.
So yeah, it doesn't. I also got the numbers for leaves. Surprisingly difficult to find these numbers. You would think it would be in a botany book, but no. So they vary a lot depending on what type of leaf you have.
Okay.
So most of the information out there is actually for crops, which kind of makes sense.
Yeah.
But I was trying to find things like maple leaves and pine needles. Surprisingly difficult to find.
Okay, thank you so much.
Thank you. More questions? I'm going to start. We'll just go down the line. Oh.
Hey, Lewis, I'm a postdoc in ecohydrology. Generally, I've not really thought much about human relationships with water. I was just wondering, when you start doing your budgets and you strip out all like your nutrients and your dissolved carbon, is that all like removing 100% of that ammonium from the system and 100% of that dissolved carbon?
No, it's definitely not removing 100%. So, for example, if we go back to the nutrient part, oops, wait, where'd it go? Yeah. At best, we're getting 90% removal because about, where is it? 5% is going to go through the membrane into the product water. And even for the part that's rejected by the membrane, we're not going to capture it all by this air stripping system.
Yeah, so basically I was just thinking, when you remove all that, what happens to downstream ecosystems when you rip out all those nutrients?
Oh, well, that's a good question. So in this circular system, ideally, the benefit is, like right now, where does San Francisco get its water? Hetch Hetchy, Yosemite National Park, essentially. There's a dam. If we did 100% wastewater recycling, we probably wouldn't eliminate the imported water, but we could substantially reduce it and potentially just use local groundwater even. In that case, that water could be reverted back to a natural river. And there's actually a lot of fights going on now in California and actually mandates by the state government to say that you have to maintain a minimal level of discharge in the rivers. So about what they're targeting is 40% of the base flows of the San Joaquin River, which is kind of one half of the Central Valley of California. So a lot of these cities that are operating these dams are going to have to figure out a way to reduce their usage to give back these waters to the ecosystem. So ideally what you're using is allowing these natural rivers to flow again into the ecosystem. From the treated water point of view, the goal is you're doing something unnatural. We're putting a lot of human waste as an overlay on top of what's in a natural water supply. And that creates imbalances, so you start generating things like algae blooms that shouldn't occur naturally. So we have to remove them. If we do something like reverse osmosis, you're generating essentially deionized water. Maybe that's too much, but we're not sending that to the ecosystem, we're sending it to us.
Great, thanks.
Hi, I'm Bowen, and I'm a PhD student in ecohydrology. So my question is, because you mentioned about that Orange County treatment plant, I heard that they actually treated the water as like potable level, but they reject it into the groundwater aquifer.
Yes.
Like because like the public may concern like if they use that directly. Do you think that may be a better way, to make this idea more acceptable? Like,
yeah. So going back to this, I mentioned before that. I'll explain some terms here. Where'd it go? Here we go. Yeah, right here. This I mentioned about this scheme. So you're right. Current systems that do potable reuse, like Orange County, clean the water up to make essentially deionized water, and then they dump it back into groundwater or into reservoirs, and then it goes to a drinking water treatment plant, is treated again, and then sent out to the consumer. That's called indirect potable reuse, and part of the motivation of that is public fear, right? And actually, the people who operate these systems talk about this from a kind of sociological point of view. It breaks the link to the toilet if you see it come out of the ground. it's hard to remember that, well, it went in from a toilet over here and then went out through the well. So what this is all about, this down here is emerging regulations for what they call direct potable reuse, where you don't have to do that anymore. And they have different flavors. A lot of the current ones like San Diego are looking at are, what if your reservoir is just really small? So you're still doing that. You're dumping it in a reservoir, but it's a really small reservoir, so you don't have more than, say, 3 days of residence time in the reservoir. And then it goes into the drinking water plant. But what we're hoping to do with our local city is called a treated water augmentation. That's the ultimate, where let's take the scenario of San Jose. All the reservoirs are in the hills around San Jose. They flow down to the city, get used, and it all flows to the bay where the wastewater plant is and where this reuse plant will be. Then, if under current systems, you'd have to pump it back up to the reservoir for retreatment. So all that energy to put it back up on top of these hills, right? So and the fact that you cleaned it up to DI standards, why would you dirty it again by putting it in a reservoir just to retreat it, if you think the water is actually of high quality? So what they want to do is direct potable reuse or treated water augmentation, where ultimately you could pump it directly into the distribution system that's near you, and you avoid all that pumping cost. And so what we're hoping to study with our local city is what effects does that have on your distribution system? Because now you have conventional water that's got organics, salts, all that other stuff, and then you have DI water that you're blending into the system. What does that do for like corrosion deposits and biofilms and all this other stuff that show up in distribution systems? But this is where, for that type of practice, this is where the government wants to put in this longer string of treatment processes, but the question is it really necessary?
Okay, thank you.
Hello, my name is Jovan. I am a PhD student in Eco-Hydrology Research Group, and I have 2 questions. First of all, if we want to use those anaerobic treatment in temperate regions, do we have some additional challenge, especially if we take in consideration that maybe the growth of microorganisms limited in that area? And the second question is, I saw that in this circular process you used sodium hydroxide, and for production of that component you also need a lot of energy. When you talk about energy efficiency, do you also take in consideration that or no, and to what extent in that way the budget will change in terms of energy?
Sure. So for the first question about temperate, you're right that California, it's always a sunny day. But in the first place that this was piloted and actually developed, this anaerobic membrane bioreactor was in Korea. So they essentially have experience with cold weather, and it operated fine. One of the nice things about it is, since it's a attached growth process, it's actually a very stable biological treatment process. So they've even tested, you could turn it off for a couple of days, just let it sit there. And then when you want to turn it back on, there's not a startup period. So it's a very reliable process. For the second question about sodium hydroxide, that was essentially, let me get back to this. These treatment chemicals, these bars right here, are those chemicals. It's mostly due to the pH adjustment needed for acidification to get it to convert to NH4+, so it can be rejected by the RO membrane, and then the hydroxide here, and then the acid to capture it again. So that's most of what those chemicals are. So yeah, I mean, it does add to the cost, but overall we're getting, what did I put in here? A minor net benefit of the entire system from a cost point of view, but a greater benefit from a greenhouse gas point of view.
You talk like an economist. I have another question here.
Okay.
Hi, so my name is Raisa, and I'm a PhD student in Earth and Environmental Sciences. This is a great, interesting talk. My question for you is, so one of the challenges you have in this process is just refining the sulfides, right, from the system. And that reminds me of a challenge also, a similar challenge also in petroleum mining, where there's a lot of sulfides that get oxidized, right? And then it sours the petroleum, right? And then, so is the refinery process kind of similar to that process? Can you just comment on that a little bit?
Yeah, so you're right that petroleum also has the same sulfide issues, and they've developed processes to recover it. Oftentimes it's like elemental sulfur. It's mountains of these kind of yellow piles that show up at oil refineries. And actually some of the techniques we're using are based on the petroleum schemes. So for example, if one of the things we're looking at is anion exchange as an alternative. I didn't look at the air stripping, I mentioned air stripping here, but an alternative is just to have anion exchange, get the sulfides, then you further concentrate it when you regenerate the system. But what do you do with all this super concentrated hydrogen sulfide? And that's where you're up near kind of petroleum levels. So the levels in petroleum are much higher than in the wastewater. But once you concentrate it, maybe some of those techniques could apply. So we're looking at some of the schemes that people in that field have used, such as kind of like iron that can oxidize and cycle if you have it in a chelate form. And just seeing if that's a viable system or not. But a lot of the challenges for wastewater is that it's more dilute than a lot of these other systems. So for, with this anaerobic membrane system, it's not rocket science or that innovative in the sense that we already do anaerobic treatment for biosolids. We do it there because it's already concentrated. And people use, even on the industrial scale, like say a fruit juice factory or something of that nature that has very high organics, will even do anaerobic treatment with fermentation for treating the dissolved fraction of organics. The challenge for municipal wastewater is just it's much more dilute.
Hi, I'm Kevin. I'm a PhD student in geochemistry. I have a similar kind of follow-up question I was curious about the sulfides and the sulfate too. You've been talking about the challenge of the sulfides afterwards, but I was wondering, like, is it just strictly because of the order of the processes that, like, has anything been looked into removing the sulfate first?
Yeah, again, we're hoping to look into that, and one of the thoughts was anion exchange. The challenge is you take primary effluent with all the concentrated organics, is it just going to quickly gum up the works? The potential benefit is sulfate is divalent, and divalent things tend to absorb more efficiently than, say, HS-, which is monovalent. So maybe we get a benefit that outweighs the competition from the organics. I highly doubt that, but we are planning to look into that as an option. I'm not a microbiologist, so my microbiology collaborator on this is trying to look at, are there ways to poison the sulfate reducers? Because in addition to having to deal with the sulfide, the other downside is you had latent energy that went into sulfate reduction. If you could stop that, then everything would go into methane generation and you'd get more energy out of the process. So are there ways to kind of poison the enzymes of the sulfate reducers? But the reason it happens is they get a little bit more energy than the fermenters out of when they consume the carbon, so they outcompete.
Right, yeah, I was just gonna say, like, so I work in mining and mine water, which is quite different, but very high sulfate concentrations is quite common. Mm-hmm. So I would maybe suggest like looking into some of the mining literature as well for like techniques for removing sulfate from water.
Yeah.
Mm-hmm. Thank you, Kevin. Last question. Another economist.
Hi, my name is Ahmed from the Department of Economics. And my question is not about the chemical part because I try to get used to and try to understand what you have explained. But the thing is, assuming that the regulators accept such circular model rather than the conventional model, first of all, how long it takes to implement such wastewater treatment centers, and the second one is what will be the length of the return of the investment, because here we have the the net benefits, but it will be costly to implement such treatment centers. So
Yeah.
do you have any estimations, or maybe
Well,
you have not?
Well, I should say I'm not an economist, so it will be more of an opinion, or hopefully an informed opinion. But the first plants, the Orange counties of the world, had to put in a lot of effort to get over the regulatory hurdle. Now things have changed, where since they've been operating for almost 50 years, that it's more standard. It's almost like there's a go-to permit. If you do indirect potable reuse, that percolation into groundwater, provided you're not some small town that the regulators would suspect would not have the capability of operating it responsibly, you're almost approved right out the door. Of course, any civil infrastructure takes years to build and construct, but it's not like it's going to take 20 years to implement, except for one thing, which is, I mentioned about San Diego having their initial project rejected. What they've now come to understand, and a lot of the effort goes into these public relations companies to try to convince the public that it is safe. And so that might take, so where we sample in San Jose, for example, is a demonstration plant. It only makes about 1 million gallons a day, and it takes the RO permeate and blends it into their non-potable reuse stream for golf course irrigation. But why do that? It's a lot of money for golf course irrigation. It's really about bringing school groups in to show them how fancy the process is, and here's your original brown sewage water. Here's your, this. Well, that's not water, but clear water. And in actual, so Orange County, you can drink the water at the end of the process. They've bottled water, and you can sample it right there, and so the public gets comfort to help kind of speed the process through. Where the delays are places like when you want to do something new, like this direct potable reuse directly into the distribution system. But California, realizing that now that droughts are the thing, the governor is basically forcing the regulators to move fast. So he combined a bunch of agencies, because part of the problem was you have one gang of people who deals with the wastewater plants and a different gang of people who deals with drinking water plants. How do the two get together and make a reuse system? So he basically took a whole bunch of separate agencies, smushed them into one, and gave them firm deadlines. Like, this isn't an if, it's a when you're going to come up with direct potable reuse regulations. And what happens in California, other places, I won't say always adopt, but frequently adopt. So that they put in the effort and other people learn from it.
I'm afraid we have to stop here. It's almost 1/2 the hour. Thank you, Professor Bill Mitch, once again. Let's give Professor Bill Mitch one more round of applause.
Thank you.
Thank you very, very much.